We're talking again about wireless communication. Wireless communication via light, and that is different from wireless communication via radio. Radio waves and optical communication. Lev, Azarkh, that's a topic that you're studying?
Yes, that's part of my research. We study a LiFi system, an indoor system where we do research on what is better. Is it using LEDs? Is it laser? Or is it radio communication? And how they behave differently. Because there's some differences that are not so trivial and were confusing at first.
They're almost like a paradox, because
Yes.
some of the results of what you should do in radio communications are different from how you should build a good optical wireless communication system. Nonetheless, I see a lot of papers where people borrow, between quotes, borrow the theory from radio and then apply that to an optical communication system.
Well, in some cases you can also do that, but what we're going to describe here is why you actually shouldn't be doing this, because there are some fundamental differences that makes all things very different from the radio communication in LiFi systems.
And one of the differences is that in radio communications we have an antenna, in optical communications we have an emitter, a laser or an LED.
Some would suggest they behave the same, but they are actually not, and we will describe it a little bit later.
Okay. And then what we will discuss is what is the best way to reach a number of client stations. Assume that we want to broadcast a message, that we want to reach all of these potential listeners. And how should we do that? Which is different in a social setting, which is different in a radio setting, but also different if we do that in optical wireless communication.
Yes, because you would think that if you have the same message for everyone in the room, it would be much faster and a bit more efficient if you just stand up and shout across the room and everyone gets the message, rather than going to every person separately and saying to them this particular message. But in radio, it's a little bit different, and in LiFi, it's also different.
It's even completely different in life.
It's very different.
Yeah, so let's see how that differs, and let's take a couple of examples. It's almost like a paradox what comes out, so that's why I like to share that. And let's also see whether we can confuse our viewers at all.
Let's see.
Because it is a bit confusing.
It is.
What are we comparing?
Well, we'll start with a system that is limited by Poisson noise. And let's say a receiver needs to receive 20 photons per bit. And we should also note that we have a limited transmit power. That's a big limitation that we have. And in such system, we don't really know where the user is or where the users are in the area. They're somewhere within our coverage area. And we have two things: is should we send a wide beam, or should we divide our area in the smaller sectors? For example, 3 sectors like we
If I
have
spray
here.
my photons all over, I need a lot of power for that. But if my power is limited, then it takes a long time before any one station has got 20 photons for the bit.
So you would think, and it's very, reasonable to think so, that if you just shine an LED into the room, it is the fastest way to reach the user, if you don't know where he is. Mm-hmm. But is it?
Surprisingly, it is not. And the weird thing is that basically by spreading it all over the place, I have to transmit so much slower that I cannot transmit very fast. Whereas if I send it in a sector of width of, let's say, 1/3 of the area, I can go 3 times faster. But on the other hand, I have to do these 3 sectors sequentially. And therefore it goes 3 times slower, and these 3 and 3 exactly cancel each other. The rate is 3 times faster, but I have to do it 3 times.
Which is very interesting, because now we have the difference from the, let's say, social setting, where just shouting into the room will be the fastest way to get the message across. Well, here, it doesn't really make a difference if you're going to go to each of the users, or if you're going to spread your whole message over the whole area.
All right, and then let's move on to our radio communication systems. Additive wide Gaussian noise, that's the typical channel.
Yes.
And now let's assume a very wide bandwidth.
Well, unlimited bandwidth.
Which it is a bit weird, but on the other hand, if we are moving towards communication systems at higher and higher frequencies, millimeter waves, these signals do not go through the wall. They stay inside the room, inside the space. If I use terahertz there, I can use huge spectrum.
Yeah.
So therefore bandwidth is not a limitation.
Yeah, no.
And then, even if we look into the Shannon equations,
Yeah.
the rate becomes proportional to the power that I have.
Yes.
I just need a certain energy per bit.
Yeah.
Okay, so what should I do then?
Well, in this case, we also need to receive a certain energy per bit. The same with we have to receive a certain number of photons in the previous system. In this system, we need to have a minimum energy per bit, and we also have our limited power. And in this case, you can see that both systems are also equally fast.
Let's do the math. We have a reference system that covers the entire room, and I get a certain signal-to-noise ratio. That's one side of the equation. If we go to the other side, we have a system where we have a sector that covers 1/3.
Yeah.
So it's reasonable to say that the power gain, the energy gain, is a factor of 3.
Yes.
My signal-to-noise ratio goes up by a factor of 3.
Yeah.
My bit rate goes up by a factor of 3.
Great.
But I have to transmit sequentially in each of these 3 sectors.
Yeah.
Why sequentially? Simply because otherwise I would use more power.
Yeah.
And that's why I have to wait until I have used my power in the first sector and then go to the next sector. Okay, so it doesn't matter.
Well, in this particular case, it doesn't really. We should also note that we assume that there is no time for, let's say, mechanical steering or steering the beam from one sector to the other.
But in radio, that can be done fast.
In a radio, yes.
Okay. So let's move on then. If we have seen indeed here that these 2 systems are equally fast towards a LiFi communication system.
Well, in LiFi, it's a little bit different because we do not have an antenna. We have an LED or a laser, which behaves a little bit different than from antenna. Because antenna we usually consider as a resistor because it has, let's say,
50 ohms.
Yeah,
If it's
50
not
ohm.
50
Everyone
gets
knows.
very nervous.
Yeah.
And then, yeah.
But can we do the same with the LED?
Well, the LED typically needs, if it is a blue LED, 3.5 volts. So that's a fixed voltage.
Yeah.
And but the current may vary. But it's always approximately this 3 volts.
Yeah.
Which would mean that the power that goes into the LED is here, let's say, proportional to the current, not to the current squared.
No, to the current.
So that's one difference. I need a certain voltage.
Yes.
And then we also have a difference on the other side.
Yeah, because in radio communications, antenna, but here we have a LED or the light source and a photodetector, which also has a conversion electrical to optical on the transmitter side and optical electrical on the receiver side.
And when the photons comes in, it kicks an electron.
Yes.
So the photon flow, which is the optical power, is translated into a current.
Yes.
Power is translated in a current. And then I have an amplifier. And at the end of the amplifier, I measure signal-to-noise ratio. Signal power to noise power. But signal power is current squared. So I have a optical power that's coming in.
Yes.
And in this transimpedance amplifier, the output electrical power is the square of the optical power.
So if I were to square an optical power, I quadruple my electrical power. Does it really behave according to the law of conservation?
You're asking the critical questions here. Eh? Yeah. At the transmitter, we were assuming that, more or less, that the LED behaves according to the law of conservation of energy. And we have very wall-plug efficient LEDs at the moment. And even for modulation, we could design the system such that we are relatively close to that law of conservation of energy. At the receiver, we have a DC power that powers the transimpedance amplifier.
Yeah.
So indeed, we have to satisfy the law of conservation of energy, so we need extra power from the amplifier.
Yeah.
And that's
where it
the
comes
system
from.
is.
Yeah.
But we have that behavior. So it's
Yeah.
better for a short time to push a lot of optical power because
Yeah.
that pays off in a much higher electrical power.
Yes.
So it makes sense to transmit at high power to your target receiver.
Well, let's see how it behaves in the optical system. The similar idea that we were exploring before with the radio systems.
Mm-hmm. Again, we can build that optical LiFi system that covers the entire room.
Yeah.
I would use quite a bit of power, but since my power is limited, I have to reduce the emission power.
Yeah.
Let's call that a reference signal-to-noise ratio.
Yes.
And then we make smaller beams. We sectorize it. And A good thing to do then is to put all your power in one sector and then sequentially go to the other sectors.
Yes, which again is very different to what we had in a radio system when it didn't really matter if we just spread the whole energy throughout the area, or if we go from a sector to a sector, because it was cancelling out the increase in the power and the different sectors or the number of sectors. Well, here in the optical system, because of this optical to electrical conversion, it doesn't behave the same.
We get three times the current, 3 times the optical power in our system. We get therefore 3 times the current, so we get 9 times the power. I can transmit 9 times faster.
Which is much, much more than we had in the radio.
9 times faster, and I have 3 sectors. So it takes 3 times longer to cover these 3 sectors, but I can go 9 times faster.
Yeah.
And therefore it's 3 times faster to go sequentially.
So in general, it was very confusing in the beginning for me and very counterintuitive that shining the room to find a user or to transmit your message to a user that's in unknown position in the room is not really faster than just going a small narrow beam and scanning the whole area and transmitting that message this way.
That's weird, because in a social setting, I will not go to everyone one by one to spread a rumor.
Exactly, but in a LiFi system, not only you can do it, but you should do it because it's so much faster.
You have been studying this and also sending that in a publication for an interesting conference.
Yes, we presented this work at the PIMRC conference, where we explored the localization system and how we can find the user, applying what we were just describing, sectorizing the coverage area into very small sectors and sending message not discretely but separately to each position in the coverage area.
And you've been using that for a system that searches where the user is, and after that you can direct that beam specifically to that user. What you even said there is not use 3 sectors, but use a very thin laser beam to scan the entire area very rapidly. And that is faster than spreading your beam widely.
Well, we can even see from the math that we had before, if we had 3 sectors, we're 3 times faster. But if we had 4 sectors, we're even more faster. And if we have like 1600 sectors, we're even more faster. Therefore, it makes sense to sectorize as small as you can.
And in that paper, of course, we need also to take into account that there are certain limitations to the bandwidth, etc., etc.
Yes.
So if people got also confused or like this paradox,
well, they should definitely check out our paper to read it through in a bit more detail, how we describe and our approach, how we went through. If you're very interested, also cite this paper, and of course you should subscribe to this channel because there are quite a lot more interesting topics coming up.
And we are looking forward to your results being seen in a full PhD dissertation. Success with that.
Thank you very much. Thank you for having me.